Hello, everyone, and welcome to our first webinar of 2023, Viscosity of Water-Soluble Polymers Formulated for Oil and Gas Applications. Today, Riosense application scientist Christian Ochoa and Soha Shabani-Verki will be joined by oil and gas expert Dr. Carl Aften of SNF Holding Company. Today, we will be presenting steady shear viscosity data for low concentration polyacrylamide formulations with and without NaCl added. We'll also be sharing shear rate sweep data, discussing factors affecting viscosity measurements for friction reducers, and we'll provide a recent study on various friction reducer viscosities with variables, ionic strength, shear rate, and product loading. Dr. Aften will also provide a general insight on the various factors that can affect viscosity measurements and how the friction reducers respond to those factors, along with his perspective on the use of viscosity measurements for oil and gas applications. And without further ado, it is my pleasure to turn it over to our speakers.
Hello, this is Carl coming to you from Georgia. I'd like to welcome you all. I'd like to thank Riosense and SNF for allowing this collaboration to go through. Next slide, please. Okay, so what is hydraulic fracturing? I know a lot of you might be familiar with this discipline, but some might not. Basically, it's just the injection of a water-based fluid under controlled high pressure that creates fractures in the rock, in the Earth's crust, where the layer of hydrocarbon is present that we want to extract. One of the things is that when we fracture the rock, we want it to stay open once we release the pressure, because once you release the pressure, the Earth wants to close any cracks. So we have to put something called proppant in it to make the cracks not completely closed so we can increase the surface area of the hydrocarbon delivery. And typically sand is used. It's essential for all the oil and gas trapped in low permeability formations to be able to make it to the surface of the Earth so we can process them. And a lot of people think that hydraulic fracturing is a method of drilling or constructing a well. It is not. If you want to find out a little bit more about hydraulic fracturing, you can go to the Riosense blog that has been recently written. Next slide, please. Okay, so here's just a simple cartoon of what's going on. Basically, what you have is, if you look at the very bottom right, in that colored zone, that's the area that we're interested in extracting the oil and gas, and those little black lines that look like hairs are actual fractures in the earth. And if you go up just above it, it's a big blow-up cartoon of what's going on. Basically, what we'll do is we'll pump water and sand with a few chemicals, and it'll fracture the rock. And like I say, the sand is called a proppant. It keeps the fissures open, which are in the dark brown. The cartoon of this little blow up is a little inaccurate because it shows a lot of sand flowing back to the well. We don't like that. That's called sand production. We like the sand to stay in the dark brown areas. Next slide, please. So this is basically just a pie chart of what goes on in the fluid of a hydraulic fracturing. 90.6% of it is water, and another 5% is pretty much sand. So that leaves only like 0.4% for all these chemicals to go in. And the one I'm going to be talking about is called the friction reducer, which is put in at 0.08%. Even though it's a very small amount, it really does a lot of benefit when you're trying to do a hydraulic fracturing. Just to let you know about the fluid volumes that we're typically using, they're always typically over 1 million gallons. Right now, they're up to 15 million gallons often. The pressures that are used to crack the rock are around 10,000 PSI, depending on how strong the rock is and how far the well is going down into the pay zone. The pumping rates, you know, if we want to say they're like 630 to 6,300 gallons per minute, and that's all going through a pipe that's around 4 to maybe 6 inches in diameter. And for all you fluid heads, the Reynolds numbers are typically above about 1 million. So that means that you're very much into turbulent flow, but you're into a flat line. If you look at the Moody chart, wall shear rates are typically in the thousands. Next slide, please. So this is basically the friction reduction phenomenon is discovered by Toms working for the US Navy, and this was used for torpedo and submarine work back then. Reduces the horsepower to deliver a constant volume of flow. So let's say we're at 100 barrels a minute, and let's just say it took 100,000 horsepower. Now what we can do is bring less engines on site, and maybe for 40,000 horsepower, we can push the same flow. Or if we want a higher flow rate with the less number of pumps, we can also do that. And the proppant transport has been related to shear viscosity and viscoelastic properties. Friction reduction now has also been related to extensional viscosity, which is something that Riosense's group will discuss. And friction reducers, when we use these in the field, there's a whole bunch of brines, salt waters that we have to worry about. You know, in the lab, we'll test quite a few salt varieties, but you always have to make sure you're tuning your friction reducer and additive package to the specific salt that's there. Next slide, please. Okay, so one of the things is these are high molecular weight acrylamide copolymers or terpolymers or higher polymers, but they're polyelectrolytes. They're not non-ionic typically. Typically, they're made by inverse emulsion polymerization, which means that we make the polymers in a emulsion which is water internal and oil external. That's done so you can deliver these polymers for very low viscosities to the delivery site. The molecular weights of these are so high that it's very hard to use any analytical technique besides viscosity to help even try to determine the molecular weight of these polymers. Typically in the friction reduction world, we're saying they're like 5 to 40 million. And to measure that with traditional instrumentation is awfully difficult. So viscosity extrapolation is used. I want to say when you measure viscosity, everybody thinks that it's really easy. You put a liquid in and turn on the instrument and it gives you a number. But when you're looking at these very high molecular weights, many things come into factor. One is your polymer, when you put it into water, it has to come out of the oil-water emulsion. And everything is extremely concentrated in that emulsion. Do we have discrete random globules of polymer? Or do we have discrete random coils? When you have discrete random coils, that's when you can do instrumentation techniques like diffraction and everything. And also these polymers are highly entangled. So in order to go into a free coil state from a glob state, it takes lots and lots of time, sometimes hundreds of days if you want to do things into equilibrium. And you know, when you're studying molecular weight, you're always talking about thermodynamics and equilibrium. There's also the dynamics of mixing time. How long did you mix it? How long did you let the polymer age? There's all kinds of assumptions that we make. Hey, is there bob slip going on? Is the acquisition time sufficient at whatever shear rate? That is very important when measuring these, because a lot of times people are very interested in low shear rate properties. What's the current diluted polymer state? That's very important. And we use the MEMS technology that Riosense possesses. And if you look in MEMS, sometimes you even have to worry about relaxation time before you start running the test. Environmental effects always affect these water-soluble polymers, like I have listed: temperature, pH, brine type, total dissolved solids, which is basically dissolved salt. Things I didn't mention here are total insoluble solids, which is called TSS. Hardness, because a lot of these are anionic and they have carboxylate functionality, and you know carboxylates don't like hardness. If you see that, they'll bind up with it and probably fall out. Ionic strength is very important on how you classify your brine. Redox potential is also very important in these. What type of measurement device are you using? Are you using a very fancy controlled stress strain rheometer? Are you using what we call a pickup truck worthy Coet fan device? Or are you using MEMS chips technology? Next slide, please. So we have here is just a very simple diagram showing concentration in log scale on the x-axis, going up to 100 weight percent, and molecular weight on the y-axis going up to 100 million. And what we see is if we look at standard polyelectrolytes, we see the C star, which typically stands for overlap concentration. That's where they're starting not to interact coils with each other. And with polyelectrolytes, that C star is pushed to a much lower level for dilute semi-entangled states. And we have to keep that in mind when we're testing. Friction reducers, what the range they're in is typically shown as in that blue box. Next slide, please. And here's a typical, what we call viscosity shear rate curve. You notice everything is in log scale again. This is called a Carrel-Usada model. And so we see basically two plateau regions, one at very low shear rate and one at very high shear rate. In the old days, measuring very high shear rate was difficult until RioSense technology. Measuring at low shear rate is still very difficult if you don't want to have enough acquisition time. And then in the area, because it's a log-log curve between the two plateaus, it's what we call a power law index fluid, and that's how we can check a lot of things in a certain shear rate range that's being used in the field. Next slide, please. So brines in general, just want to say when we talk about brine, we're not just talking about simple sodium chloride or potassium chloride. There are all kinds depending on the formation. And how do you characterize that brine? All kinds of ways. We typically run ICP analysis to do that. But the thing is if you raise brine type, since these are polyelectrolytes, you get more shielding of charges, which is the Debye-Huckel theory. Sometimes you can have bridging, like we say, with hardness and anionics. What that'll do is alter the solubility elasticity. So are you really measuring all the polymers there, or you're actually measuring a different type of polymer? How do we measure that? We do hardness from the old method in calcium carbonate. Recently, we've been doing a lot of work with ionic strength, which actually takes in how many ions are being put into solution and what is the charge to the square. And then we look at R+ ratios of cationic multivalent times all multivalent. And at the bottom, just remember again, all these things you have to worry about when you're measuring this. And next slide. And just for your grins, what I did is I took some typical brines that we typically run when we run these FRs. I'll describe an FR curve later in the talk. But as we see on the top, we have in the legend, we have fresh water, which has very low TDS and very low ionic strength. And as we move down in that legend, our amount of TDS increases to 300,000, which means it's 30% salt. That's pretty significant. And the ionic strength is like 6.5 molar. But what's kind of interesting, if you look at this curve, it's kind of linear. And that's kind of saying that the Earth's formation kind of comes into these equilibrium standards between divalent and monovalent. You'll see one point actually at the 150,000, a little below the line, but that's kind of what we call an artificial brine of 15% KCl, which is a monovalent. Next slide. And I think you're taking over.
Okay, thank you, Carl, for giving a very informative and interesting introduction about hydraulic fracturing in oil extraction applications. Now, before we share the data we have collected, I want to give you some quick background on viscosity and talk to you a little bit about our technology that we use for measuring viscosity. As you know, viscosity is the resistance of a fluid to flow. For example, highly viscous fluid has a higher resistance to flow than an inviscid fluid. The viscosity can be defined as the shear stress experienced by a fluid divided by shear rate or rate of deformation. In this diagram, you can conceptualize the shear rate as the velocity gradient perpendicular to the direction of flow. Another way to think of shear flows is to think of them as adjacent fluid elements moving past each other at a different velocity. At the nano and microscopic level, the viscosity of the fluid is the molecular friction between, say, molecules, particles, or self-assembled structures. Viscosity can be sensitive to what's happening at this level and can inform on the microstructure of these elements. Now let's go over how we measure viscosity with our VROC technology. Our VROC technology is different than rotational instruments and gravity-driven capillary tubes. VROC stands for viscometer rheometer on a chip, and it's a combination of microfluidics and MEMS or microelectromechanical systems. It consists of a rectangular microfluidic channel with 4 pressure sensors that you see that they are linearly aligned along the base of the channel. We control the flow rate through the channel and monitor the linear pressure drop along the 4 pressure sensors. From the flow rate and fixed channel dimensions, we calculate the shear rate, and from the slope of the pressure drop and channel dimensions, we can calculate the shear stress. So we take these values of shear rate and shear stress and input them into this equation and calculate viscosity. So this is how the core of our technology works. So with that in mind, now let's take a look at the instruments we have used. The VROC technology is embedded in our viscometers. The viscometer shown here in the left is the Initium 1 Plus, which is a viscometer we use to get our data for this webinar. This is a temperature controlled instrument that allows for high throughput and automatic measurements. To start, you place your prepared solutions either in a 96 well plate or in Waters vials in a 4D vial rack. After setting up your experiment in our easy-to-use software, the instrument takes care of the rest of the steps. That includes loading your sample for measurement, measuring the viscosities, and cleaning all the relevant flow paths, syringes, and needles. What the system can do is to use its auto-sampler to automatically load samples from a sample tray to the test syringe via this injection port. The syringe that loads the sample is then taken to the cleaning port for through cleaning. This cleaning involves 1 to multiple solvents which are stored on the left in 3 separate solvent bottles. The solution in the test syringe is then introduced into the chip and pumped at a desired shear rate for viscosity measurements. We have multiple chips, which include the A, B, C, and E chips. B chips are the most useful with the number of samples they can test. E chips, on the other hand, are more appropriate for higher viscosity samples. For our measurements, for the experiments we have done for this webinar, we used a combination of the B and E chips. You have the option of selecting a retrieval feature in our software. What this means is that after the test syringe pumps all the solution past the chip, it then pumps in the opposite direction to retrieve solution. This allows you to perform lots and lots of measurements with only one loaded solution. After measurements, the system cleans all these flow paths, removing any traces of your tested solution. Again, this is done with 1 or multiple solvents shown on the left here. Most loading and cleaning protocols that you will need already come pre-installed into the system. You just hit the drop-down menu in the software and choose the right one based on how much sample you loaded and how viscous your sample is. But if you want to modify these loading and cleaning protocols for your particular sample, we strongly suggest you contact us to help you with that. You can also contact us if you want help with making measurement protocols for your particular samples. Apart from the Initium 1 Plus, we use the VROC viscometer, which is another small sample viscometer that allows for a wider range of shear rates and up to 1.5 million inverse second. Like the Initium, this is easy to use. You load your sample into a Hamilton syringe, connect it to your chip, and place it into the temperature-controlled syringe jacket. Once you close the jacket and lock the pushing block, you are ready to start designing the experiment in the software and run the sample. You have the option of using a 10 ml syringe and jacket, which, as I mentioned, allows you to go up to the shear rates of 1.5 million inverse second. Now I'm going to go over the viscosity data we have collected with our VROC technology, with our Initium 1+ and VROC instruments, and share some results with you. The samples we tested for these experiments are provided by SNF Holding Company. So the first sample we tested is 0.28% polyacrylamide in tap water, and this figure shows the shear viscosity as a function of shear rate for this high molecular weight polymer. In order to have a broad range of shear rates, we used different VROC chips, including BO5, BO35, EO2, and B20. Different channel depths and pressure full scale of these chips allows us to cover an extended range of shear rates. We ran these experiments on Initium and VROC, as I mentioned, with higher sample volume. VROC allows us for a wider range of shear rates. As expected, this high molecular weight polymer exhibits shear thinning behavior such that the viscosity decreases from say 13 to about 2 millipascal second, as the shear rate increases from 500 to 700,000 inverse second. Adding polymer to an aqueous fracturing fluid reduces friction and improves the efficiency of oil extraction process. The second set of samples that we tested are polyacrylamide in 1 molar NaCl at temperature of 25 degrees C. If you leave the sample sit for a day, it will separate into a white substance in the bottom and a clearer solution on the top. This separation is caused by the addition of salt. What we did is we performed 2 sets of measurements. For one set, we gently shook the solution to mix the white substance with the clearer solution. We then used this solution for measurements, which are shown in the plot on the left. For the other set of measurements, we took the same solution, centrifuged it at 12,000 RPM, and took the supernatant. We then performed the measurements on this centrifuged supernatant, which are shown on the plot on the right. In addition, we used the Initium and VROC with the B and E chips with multiple flow channel depths ranging from 20 to 200 microns to access a wider range of shear rates. The results show that the apparent viscosity decreases with shear rate for the entire shear rate range probed. For the sample that is not centrifuged, the results obtained with the BO5 chip on the Initium and VROC show this plateau at intermediate shear rates. This is something we have observed before for samples with polymer metal cellulose in tap water with added surfactant. Also, these results show less agreement with the data from the other chips. For the sample that is centrifuged, we see that there is less agreement between the chips. This may be caused by differences in the centrifugation between the multiple volumes tested in the multiple chips. Now let's take a look at the shear degradation of these polymers. For these measurements, we exposed the polyacrylamide in tap water as well as the polyacrylamide in 1 molar NaCl to shear rates on the order of 1 million inverse second. For each segment, we ran a long viscosity measurement at this elevated shear rate such that we passed the entire volume of sample through the chip. On the other end, we collected the sheared sample in a clean vial for the subsequent segment. In total, we performed 7 to 8 segments of this. Essentially, we exposed the sample to cyclical high shear rate. What we found is that the relative viscosity decreases with segment number for both samples. And the relative viscosity here is with respect to the solvent used. So for the sample without added salt, that solvent is tap water, while for the sample with added salt, that solvent is tap water with 1 molar NaCl. The relative viscosity exhibits a larger drop for the first segments, but followed by a plateau. These results show that exposing these samples to such high shear rates can lead their viscosity decline, which can lead to poor performance in oil extraction applications. So, like shown in the previous slide, there are viscosity decline measurements. For this, we focus on the sample with added salt. What is different here is that we expose the sample to cyclical high shear rate 1 day, followed by additional cyclical high shear rate either 1 day later or 1 week later. The results show that the viscosity is not recovered after 1 day or 1 week of exposing the sample to cyclical high shear rate. This indicates that the sample has experienced shear degradation or a shear-induced structure change has not reversed in the span of 1 week or less. Well, that's sort of background on the basic viscosity, our instrumentation, and shear viscosity measurements. And now I'm going to turn it over to my colleague Christian, and he's going to go over some details on extensional viscosity and start sharing some data with you.
Thank you, Soha. So before I go into the extensional viscosity measurements, we're going to go over the transient viscosity data collected with the Initium 1 Plus for these solutions of the polyacrylamide and tap water, as well as the polymer and 1 molar salt solution. So we show this for 2 shear rate ranges, one lower, one higher. And one interesting thing we saw is that the samples without added salt show this relatively large transient peak before the onset of the steady state. So for the lower shear rate, this maximum of the peak is about 60% larger than the steady state viscosity. But for the higher shear rates, this percentage is more about 30%, so that drops considerably. Now, on the other hand, for the same shear rates, the sample with added salt doesn't show these kind of peaks. For the lower shear rate, there is a small peak, but it's only about 10% different. And for the higher shear rate, we don't even see such a peak. So we think these peaks are possibly due to any yield stress from any development of a structure or network that needs to be broken down for the solution to start flowing. So apart from the shear viscosity measurements, we use the VROC for extensional viscosity measurements. So for these experiments, we used extensional flow channels. So while the shear channel that we showed in a previous slide has a uniform cross-section along its length, the extensional ones have this contraction expansion zone in the middle of the channel. So this contraction expansion is going to induce extensional flows in the chip, which we can capture with MEMS sensors. So the channel dimensions for all the extensional chips are fixed. This is not like the uniform channels, which have multiple channel depths. One similarity to the uniform channels is that we have multiple chip type options. So as you go from the A chip to the B chip to C and E, the maximum pressure the chip is capable of, the sensors, the maximum pressure will increase. So that means that you can more appropriately study samples with higher viscosities as you go from E to E. So for example, if you have a high viscosity sample, you're going to be able to measure a broader range of extensional rates with higher pressure C and E chips as opposed to the lower pressure A and B chips. And likewise, for lower viscosity samples, you're going to be able to measure a broader range of rates with the lower pressure chips. So how do we calculate the extensional viscosity from the chip? So like the uniform channel, it has 4 pressure sensors that are located along the base of the channel, which measure the pressure drop as the fluid is flowing. So there are 2 sensors before the hyperbolic contraction expansion, and as well as 2 sensors after that. And this contraction expansion is going to change the velocity of your flow, introducing velocity gradient in the direction of flow. So as opposed to perpendicular to flow, which we saw in for the shear channel. And this is going to act to stretch or elongate your fluid elements. And this is how this hyperbolic contraction expansion is introducing this extensional component to the deformation of your fluid. So to calculate the extensional viscosity, we need to get the pressure drop from the entry point to the exit point of this contraction expansion. And for this, we measure the pressure drop between sensors 2 and 3. So that's shown in this cartoon here. And then we extrapolate that to the pressure drop from the entry to the exit point of this contraction expansion. So that would be shown here by this blue profile. So this pressure drop is delta PC, shown here, and that's going to depend on the extensional contribution to deformation, which is this one. And another thing to note is that there's also a shear contribution because we still have the physical confines of the channel. So because of that, there's a no-slip boundary condition that applies to the channel walls, and this will contribute that shear contribution. So applying the extensional deformation will generate a normal stress, and this is like the analogous to the shear deformation generating a shear stress. So ideally, the first normal stress difference is going to be equal to the pressure drop to extensional contribution only, divided by the Henke strain. So the Henke strain for our geometry is about equal to 2. Now, if you have Newtonian or power law fluid, you can use analytical expressions to extract and remove the shear contribution to your pressure drop and end up with only the extensional contribution. But if your fluid doesn't behave this way, you will use the measured, you have to use the measured pressure drop, knowing that it has contributions from shear and extensional. And then the extensional viscosity is defined as this first normal stress difference that you get from here, divided by the apparent extensional rate. So the extensional and shear flows within this extensional microfluidic channels are kind of mimicking the flow through small pores and fractures during the oil extraction. So we wanted to see how the measured extensional viscosity is changing upon applying this cyclical high extensional rate to our polymer in salt solution. So we cycled for a total of 8 segments measured, and we can see the instrument gives an extensional viscosity decline with the segment number. And we think that this decline is due to the polymer degradation or a structural change that's caused by a combination of extensional flows, as well as turbulent flows in the channel. So we don't think this degradation is caused by shear in this case, because the shear rate here is too low for that. So we predict that there are turbulent flows in our channel due to the Reynolds number we calculated for the conditions experienced during the viscosity measurements. So we calculated the Reynolds number of about 130 to 300 for the viscosities. So this is actually enough to get turbulent flows in our extensional chip channel, because its critical Reynolds number for this transition from laminar to turbulent is on the order of 10, only 10. So this critical Reynolds number is this low due to the contraction expansion zone in the channel. So we think that by mimicking these extensional, turbulent and shear conditions and rock pores and fractures, we obtain a drop in viscosity. So here we show the results of extensional viscosity as a function of extensional rate for 4 passes or 4 cycles. And each cycle, so these red square data points, for example, is 1. Each cycle consists of an extensional rate sweep performed on 1 volume of solution. So the rates are going to range here from 600 to about 7,500 inverse seconds. And for these rates, the Reynolds number is well above the order of 10. So this is indicating that there's turbulent flows, which is giving this extensional thickening artifact for each shear rate, extensional rate sweep. So this is not true extensional thickening, because to determine an accurate viscosity reading, we need to have laminar flow in our chip. And our viscosity calculations are based on assumptions of laminar flow, and they're not going to be accurate with turbulent or secondary flows present. So nevertheless, using the extensional viscosity that we're getting for the first pass, the sample shows this extensional thickening followed by extensional thinning at this higher rates. And this corresponds to the degradation or the structural rate change of the polymer. So for the next pass, which is shown in purple triangles, pass number 2, the extensional viscosity is lower, and it decreases again for pass number 3. But after pass number 3, the viscosity is not going to decrease as much. So the way we've presented the data here is another way of showing the viscosity decline that's associated with the high extensional rate that we're imposing on these solutions. And we can use this data like this to further predict the extensional rate above which viscosity is going to decline due to any polymer degradation or structural changes. So now I'm going to turn it over back to Carl, who's going to resume by discussing how the data acquisition time can influence the viscosity of your friction reducer.
Okay, like we said before, this is actually for a couette geometry or parallel cone and plate geometry. Whether you have, when you say an expensive rheometer or a cheap one, they're going to show the same. And what this shows is when you typically do shear rate sweeps, you'd start at low shear rate. So here we started at 1.7 with a couette geometry. And if you would measure the reading after a minute, you'd say, follow the blue curve. Looks like you got about 3 centipoise. But if you let that RPM keep turning, after about an hour, you'll see that you're at 38 centipoise. That's probably your real viscosity measurement, because you see it staying steady. Now, if you increase, and that's over a gap of 1 millimeter, and at 1.7 reciprocal seconds, that's about 1 RPM. So it took 120 turns to hit equilibrium, because these are memory fluids. They take a while. In order to measure across a band, you have to make sure that you have a certain profile across it. But once you've bridged that profile at 1.7, then you can go up to 3.4, all the way to 13.6 that was measured. And as you see on the left, you'll see the viscosities drop. And you can tell there's kind of a log or an exponential progression, because as you go up in shear rate, the lines get much closer. So that's something that you always have to keep in mind. A lot of fancy rheometers, if you don't have this in mind, you're going to get data that doesn't mean too much. Next slide. And this is with the MEMS chip. Actually, there's another phenomenon that you have to look out for sometimes, since these are very high molecular weight. Once you push the fluid in the syringe, you want to rest it before you actually push it again to make your measurement. And what that differential time is called relaxation time in seconds. And if you see at 51 reciprocal seconds on top, you can go anywhere from 52 centipoise at very little relaxation time to 68 centipoise at a long relaxation time. So if you're measuring at low shear rate, that's going to be important for measuring this polymer. Once you hit about 511 reciprocal seconds, it's relatively flat to time, so you don't have to worry about it so much. Next slide. So in this one, what we did is we took that polymer at a certain age and measured the viscosity. And as you can see, we measured it from 6 hours to 192 hours. And this is under a controlled atmosphere, so there should be no oxidation taking place. It's just due to molecular rearrangement. And if you see at 6 hours, the amount of viscosity that you obtain is higher, especially in the low shear rate range, where that's going to be normal. But the interesting thing is, if you follow it down to about maybe 2,000 reciprocal seconds, you start to see a little bit of dilatancy, which is a very interesting thing. And as you go on in time, you see that dilatant peak disappear. So what it's saying is, overall, the viscosity is dropping with time, but probably not due to any oxidation change. It's probably due to the molecular rearrangement of the polymer matrix itself. Next slide. So here is another nice thing that you can do with the MEMS chip, is it can raise and lower the temperature within a certain range. And so if you measure your viscosity of your polymer and do a shear sweep, and we did this, is the orange curve on top at 77. And as you increase the temperature, you see a decrease in viscosity, which typically is what you expect. If you assume these are even random coil, random interaction blobs, hey, as the temperature goes up, you have entropy effects that actually say collapse in. And if you go back to the green curve, you see at 77, once you've taken it from a temperature sweep back down to the original temperature, the amount of viscosity is a little bit less. Is that due to molecular rearrangement? The only thing is, you'll say, well, what happened to the other 3 data points? Well, that happens because you can only load up a syringe once. So if I loaded up a syringe multiple times, it wouldn't be the same. Okay, next slide. This slide, I'm going to show you what a friction reduction curve looks like, and that's going to take a little bit of time. If we look at the pink itself shows the friction reduction curve. So what you see on the y-axis is percent friction reduction. What we do is we compare a fluid without a friction reducer and measure the pressure drop in that. And then we put in a friction reducer and measure the pressure drop profile versus time. All this is very controlled. What we do is we have a certain pump and a certain pipe size, so we can calculate a velocity. From that, we calculate a Reynolds number, and from that, we can calculate a friction factor, and then using Darcy-Weissenberg, we can calculate a pressure drop. And what happens is, in the lab, we get a curve that is very similar to the pink curve. So the area in shade just means the area under the pink curve. So what it's saying is that, hey, when we're running a fluid without any friction reducer, of course we get 0%. And that we run for about a minute before we go in. But as soon as we introduce the friction reducer, you'll see it increases to about 60%, and that happened in about 40 seconds. But since this is a loop, and we talked about before, you'll see friction reduction degradation over time, and that's what you see in the curve going down more to what you say maybe a flat profile where it isn't degrading very swiftly. And then what we did is we took samples out of the loop at these time segments on the bottom and measured the average viscosity over here on this axis, on the second y-axis, between 1500 and 7900 reciprocal seconds. And if we do that and superimpose it into the curve on the right, this is what we see. Of course, water itself at 0 is very low at the bottom, but at the top you see 15 seconds, 30 seconds, 60 seconds. And as time goes on, the viscosity is decreasing, but it reaches a certain level and then goes up a little bit, which I'll show on the next slide. So this is what these things are really used for, is friction reduction. We measure it by friction reduction pipe, whether it's an open-end pipe once through, or what's easier is a recirculating loop. But we were trying to see, hey, can you relate viscosity now, since we have the MEMS chip that we can go ahead and measure with good confidence very low viscosities. Next slide, please. So what we do now is we age that solution 28 days, and what you see on the left side is the 15 and the 30 second readings are giving us almost dilatancy in it. And if we go down, we'll see we reach a certain minimum at 180 seconds. Maybe at 240, you can see there's some weird things going on. But at 360 and 600 seconds, the viscosity actually went up a little bit. And if we take that curve and superimpose it on the right, what we see, these are the viscosity numbers at various pull times from the loop after 1 hour, which is the original data, and after 28 days. And what we're noticing is, wow, after 28 days, the viscosity actually increased. And of course, we kept these polymer samples under nitrogen and in a locked cabinet, so no light destruction, UV absorbance, and transferring of bonds could take place. So it's very interesting to note. If you want to, you can say, oh, that curve on the top almost looks like the friction reduction curve, but it's got a little dilatant peak at the end. I just say is these things are very hard to understand in a complete sense, and using Rheosense's technology, we might have a little bit better understanding. Next slide. Okay, the next one is I just want to show you, I talked about it's very hard to grab consistent viscosity numbers unless you do everything the same. And one of the things that I mentioned, oh boy, brine can change. So how do you measure that? Well, we did a little study recently. We've done tons of studies, but I'm just going to show this one. We took 4 friction reducers, A, B, C, D, E. ABC is anionic, D is cationic, and we loaded them in from 0.5 to 3 gallons per thousand. That's a typical way that we add liquids to liquids in the field. And then we used a brine blend, a simple of sodium chloride and calcium chloride, and we characterized it by ionic strength. So it basically went from 0.01 to 3 molar ionic strength. Next slide. And these are contour plots. If you're familiar with these, I've shown these before. What you can do is plot 2 variables changing at the same time. You can do it with multiple variables, but we can only conceptualize 2D space with the z-axis as the response. So if we have here is if we have loading at the bottom axis going from 0.5 to 3 gallons per thousand, and then we have the ionic strength increasing from 0.1 to 1.99 on the y-axis, the contour plots are viscosity. And on the left, it's measured at 5.11 reciprocal seconds. And at the right at 511 reciprocal seconds. We can run the whole gambit, but you can only show so many slides at a time. One thing you'll see is that on the left, you'll see it goes from 10 to 60 centipoise, and the curves at the higher part of ionic strength tend to be flattening out, which shows that this FR, once it gets into a certain range of ionic strength, it doesn't care so much. And since it's a shear thinning fluid at 511 at the right, all the numbers are way, way down. Now we're at going from 1 to 2, but you'll see the contours are still relatively parallel to the ionic strength, which means that this FR does not care so much about ionic strength, even when there's what we call divalent cations present. Next slide. So in this one, here's another anionic at 511 on the left, sorry, 511 on the right, and 511 on the right. And we see, hey, this one is much more susceptible to ionic strength. And also, we do not have what you call exponential rules running the contour plot. They're more linear. So you see parallel lines when you look at the contours, which means that, hey, if I move up on ionic strength, my viscosity is going to go way down. But note the viscosity in the lower right corner is probably 70 in that corner. So the total viscosity, if there's no ionic strength present, is very, very good. So this would be a friction reducer you'd like to use in fresh water, where the previous one says, you can use me in fresh water, I'll do pretty good, but if you use me in high brines, I'll do pretty good. Same thing with the viscosity on the right. If you see 511 reciprocal seconds, everything is down because it's a power law fluid, but the linearity is maintained. Next slide, please. So if we go into FRC, which is also anionic, you'll see that this one gives a behavior between A and B. So this might be, I might want to use this FR for viscosity control. And it gives, of course, the same type of reflection. So it's in between A and B in the way that it behaves. Now, if we go to a cationic system, which is the next slide, 32, what we'll see is, the behavior is a little bit more like letter B. So even though it's cationic, and you'd expect it to do better in higher multivalent brine strength, it isn't necessarily doing that. And of course, cationics cost more than anionics at certain charge realms. Next slide. Another thing that we can measure with the Couette rheometer is what is called gel strength. And that is kind of within the rheometer itself calculates things. And it gives it in dynes per centimeter. I know there might be some calculation errors in this, but when you look at the correlation functions of these surface responses, they're very good. They're actually better than the viscosities, and that's why I decided to keep them. And what you'll see is with slide 33, slide 33, I'm sorry. You'll see that the response shows a minima up at 1 centipoise, like right in the middle of the loading curve and at high ionic strength. But if you go to a higher shear rate, the numbers are opposite. They increase. And as you can see, the contours again are relatively parallel to the ionic strength, which means that this FR does not mind this brine so much. Next slide. And in this one, now we're seeing gel strength again, showing the same trends, low at 5.11, high at 5.11. And again, there is a little bit of curvature, but you can say that's a pretty linear response like we saw with the viscosity. Next slide. And this is FRC, which is also anionic. And again, it's in between the two in the responses. So that's just something to notice. So, hey, I've got 3 anionic FRs, and if you're interested in how they behave in viscosity and gel strength, they're different. And you have to know that when you're trying to apply this. And when they work as FRs, I can tell you the same thing is true. FRA doesn't care so much. FRB really cares what brine it is. FRC is in between. And if we go to the next slide, that's the cationic. And as you see now, the cationic has a whole different type of shape. As you can see, actually at higher loadings, it is much more what we saw ionic strength dependence because it's going through a section that goes upright. and a little bit of different curvature on the way the lines are bent. So it's relatively linear, maybe you're at lower loadings, but then as you go to higher loadings, it reaches plateau values. And then the final slide. So as you can read that, I know we're running short on time, so you can read that on your own. But as I'm saying, yes, when you measure viscosity, there's so many things that you have to consider. Because when someone says, I want you to reach a target viscosity, you really have to ask, how do you want us to do that? And when they give you a brine and they give you the composition of the brine, a lot of times when you put that brine together, because they did it from acid ICP, when you put that brine together, it'll precipitate and oxidize with time. So you have to make the customer aware of that. MEMS is really neat because you can get into extremely high shear rates. And also now with the extensional properties, we really might learn some good things. So thank you very much.
Thank you very much, Carl, and everyone for sitting in. So we have some questions here that we've gotten over the course of the talk. And I think we can take the first one, which is, can we test the chemicals over time to prove when they are still working or if they are sitting on site over a certain amount of time? So yes, you can test if the sample retains its viscosity over time. And this is because the viscosity is going to contribute to the performance of these chemicals. So the next question is, what does viscosity tell us about samples pertaining to viability for fracturing processes? Carl?
Well, what it does, you fall into schools of thought. Some people say viscosity is very important. And I'm talking about shear viscosity when it comes into proppant transport. Some people have said, hey, if I have a certain viscosity and a certain proppant particle size, when I get into Stokes' law type of settlement, that viscosity becomes important. If you're into what's called Newton or Allen transport, the Newton transport velocity is the only important factor, and that's at very high flow rates. And at Allen transition rates, the viscosity contribution becomes much less. So certain people say viscosity is very important for proppant transport in a Stokes realm, assuming that there's no interaction and you use the Haywood correction. And also some people are saying that extensional viscosity is very important for the way an FR can work and maybe even transport proppant. And the thing is that if you're going into proppant transport, you have to start talking about a Reynolds particle number instead of just the Reynolds number of the fluid. Thank you.
Thank you, Carl. Another question is, I think we can try answering this one. Can this testing be used for other polymers besides friction reducers, such as guar-based gel systems? These will have much higher viscosities than friction reducing systems. So yes, we think with our VROC that we can get, we can measure these higher viscosity guar-based gels. You would have to ensure that you either filter or make sure that there's no large enough particles in these solutions.
Yeah, that's a big thing, because I know when I did a lot of work with guar gum like 15 years ago, if you don't get the residue out, it's going to clog up the chip.
That's right. Yeah, we've had that, encountered that as well here. So the next question is you want to take those, Soha?
Yes, sure. Is there a viscometer that you have which is useful for on-site testing? We will need this to be portable and able to measure a wide range of viscosities. Yes, there is. We have our MacroVisc viscometer, which is our portable small sample viscometer that allows you to measure the viscosity with high accuracy and repeatability.
Yeah, and I've used the MicroVisc for years and years. It's about the size of a 2-pound Velveeta box. So it's very, very transportable.
Yeah. And the next question is, what are the temperature ranges that we can test with your instruments? For the VROC and Initium, you can test your sample in a temperature range from 4 to 70 degrees C.
Thank you, Soha. So the last two questions I see here, kind of two questions in one, and I think Carl, you can help us with this. So what does a change in viscosity over higher shear rates mean for a frac job? And the second one is, could relaxation time on your instruments allow us to better understand sense settling behavior through the fluid?
Yeah, it's like I say, viscosity is, as we say, is a shear dependent thing. So it depends where are you at in the thing. A lot of people will say, hey, when I'm at the perforations, I use 170 reciprocal seconds. And once I'm past that, it doesn't matter so much. But the whole thing is when you measure that, that's of a clean fluid. That's not a proppant laden fluid. So it makes it very difficult because nobody wants to run, of course, you don't want to run proppant through this viscometer because it won't be able to handle it. And also, even when you do a friction reduction pipe flow, you don't like to handle proppant unless you've got what you call a sacrificial pipe type of system, because it's going to change the roughness of your pipe and change the diameter of the pipe with time. So that's one part. And the other part was what? The second part was what? I forget.
Could relaxation time on your instruments allow us to better understand sand settling behavior through the fluid?
Yeah, I think it could a little bit. And it's just saying that it's a time transient phenomenon. You know, once you're in the frac and you've got a fluid moving through it transporting sand, once it rests, maybe a certain relaxation time will come into effect before things actually go when you're trying to calculate the proppant settling.
Okay, great. I don't see any other questions. I do see someone who would like to forward a copy of the presentation. Yeah, we can do that. You can contact Grace as well for that. And with that,
I think whoever signed up for the webinar will get the.
Oh, that's right. So I think you
webinar.
should receive those slides if you signed up for the webinar. And with that, thank you so much, Carl, for this great collaboration. It was really fun working with you these past few months.
Mm-hmm.
And thank you all for attending this talk and for your questions. And have a good rest of the day.
Thank you.
All right. Thank you. Look forward to working more.
Yeah, same here.